Okay, you may say you got here early and nobody else matters, or you may say they're not coming, they've lost interest. Should I start now or wait a minute or two? What? Start now. Okay, so that's good. Okay, so let's get started. At least we can do the going over the contest part again. Yesterday, the contest we had 10 problems, and the winning team was Overflowed. Is Overflowed here? Okay, where are you guys from, by the way? Argentina, okay? So they solved all 10 problems, and they got it, the last one with, I think it's 7 minutes to go?
Yes, 7 minutes ago.
So I told Tanzir for the test today, I want it 6 minutes harder, so that you guys can do that. Okay, was the test, if we go through this, was the test the right level of complexity, too hard, too easy? Okay. So that is good. Okay, so let's start by, are there any questions people wanted to go over? Okay, obviously we've got a team that solved all of them. So is there any questions people wanted to go through? Yes? F. Which one was F? Bit of merry old England. Who got that one? Okay, get up here. Tell us who it is. And again, you get to the microphone. Okay, here, let me dismember it for you.
Hola, hola. So in problem F, you had to generate a program in a very simple programming language that had only 2 types of statements. It had a variable assignment, which looks something like this, and it had print statements, which look something like this. Right? So the idea is we can assign variables and then we can print variables. And we are given some sort of sequence of numbers that we have to print. So perhaps something like 1, 2, 3, 1. And so a very simple program in this language that would work here is something like x equals 1, print x equals 2, print x equals 3, print x equals 1, and again print x, right? So is the program clear? So we were given this sequence, and we have to generate something like this, right? And there's one more restriction. We have to use a limited amount of variables, right? So they give us some number m, which is the amount of variables. It's up to 26. And we can only use m variables. And why do we care? We care because assigning a variable has a cost. And the cost is equal to the pop count, the amount of set bits in the number we are assigning it to. So for instance, this assignment has cost 1. This one also has cost 1, because these are both powers of 2. But this one has cost 2, right? Because in binary, this is going to be 1, 1. Okay? Is that clear? Excellent. So how can we approach this? I look at this, and it looks a bit like, if we look at the print statements, it looks like a bit of a path in a graph. Kind of like a control flow graph in a compiler, if you know what that is. And we say, well, here we want some variable to have the value 1. Here we want some variable to have the value 2. Here we want some variable to have the value 3, and 1 again. And what I figured is, well, perhaps what we could do is add like skip edges. And then we can cover this graph with m paths. And those paths will be the variables that we use to print at those specific points in time. So perhaps we make this path, and that means these 3 print statements use the same variable. And then we have this path, and that means this one uses a different variable, so perhaps something like y. So then the idea, and this is very much what we did, right? Of course, this is not really going to work because we need to do a whole bunch of things. But already it looks a bit like flow, right? Because we're trying to pick some one of disjoint paths over a graph, which is kind of like a flowy thing to do. So we need to ensure several things for this to be a correct solution for the original problem. So first, we need to assign every single print statement to a path, right? Like, perhaps if we just throw m units of flow, maybe they all just skip right to the end, and we don't assign a variable to any of the print statements in the middle. So we need to do something to ensure that all the prints are assigned to some variable. The way we do that is by assigning negative cost to all the print statements. So we split them into an in node and an out node, and we put negative cost, very big negative cost. So we let's call it infinity. And now if we have a bunch of flows of equal flow value, and we throw like min cost max flow, well, the min cost is going to be ones that grab all the negative infinity edges, right? So this is going to force paths that go through the prints. And I'm going to start filling out what the graph actually looks like. So we're going to have some source. We're going to have a sink. And this source is going to flow into every single print. And that sort of represents, well, a new variable is used for this print statement, and then we just keep reusing it, and that's what the path represents. And then we're also going to have edges flow into the sink, and that means this variable will never be used again, and that's when it flows towards the sink. That pretty much does what we want. Like if we throw min cost max flow, it will assign, well, if we put, perhaps we could put like an actual super source, and we can put capacity m here. If we just throw m units of flow through this network, it will assign a variable to each print statement. We're not taking into account the costs. So how can we do that? Well, we know that the cost is only when we assign, so when a variable changes value. And what we can do is say, look, here's a, we have to print 2 in this point in time, and we have to print 3 in this point in time. And so we say, well, the transition between these 2 points in time implies a variable assignment, right? So if we want to use the same variable for this one and for this one, it must be assigned in between, yes? And so we must pay the cost of that assignment. And that's a perfect place to put the cost, like right here, we put pop count of 3, which is what we have to assign, and so on. And we also put those costs at the top, because when we use a new variable, it's initially like undefined, and we have to assign it as well. And that's pretty much the entire flow. Like that's the network we built, right? Is that clear? Is that understandable? Yes.
Assigning the source to every print statement you have, and I didn't understand why each print statement is connected to one another, so we can modeling the graph.
Yes. So we're gonna model the lifetime of a variable with a path. Is that clear? And as this path goes through different print statements, the variable must have the correct value for that print statement when it goes through that print statement. Right? So we have this path right here, for instance. Remember, we're trying to print 1, 2, 3, 1. So here, it must be 2. and here it must be 1. Yes? So some variable x at this point must have value 2, and at this point it must have value 1. Yes? But if it has value 2 at this point, and value 1 at this point, it must be assigned at some point in the middle. And we are free to just do it like right here, right before the print. There's no reason not to do it. And the reason we add these edges is to allow any variable to be used at any point, skipping as much as we want in the middle. The cost is just to represent the cost of assignment. So for instance, this edge that goes from a 1 to another 1 would have cost 0. That would be free. Is that better now?
Okay, very good. I guess we clap for our people who come up here, right? Okay, good. Any other problems people wanted to see done? Okay, yes.
Can you show us a way to solve problem G with block?
Which one is this?
The armchairs problem.
The armchairs, G. So we have another volunteer who solved G. Okay, you. Okay, here. Just take the microphone. Turn it on and sing something. Is it on?
Okay, so G was you had like an array of ones and zeros, and they guaranteed that there were at least the number of ones would be greater or equal to the number. The number of zeros would be greater or equal to the number of ones. So zeros. And what you had to do was find like the minimum cost. Like you had to have every one change position to a 0. Right? A different 0. And the cost of this operation of changing position was the distance from the 1 to the 0. So it would be j minus I. And you have to like minimize the cost of changing everyone to a different 0. Yeah. So everybody got the problem. Cool. So one idea you could have had was doing a bipartite graph and doing maximum matching with max flow min cost. So you'd have like the ones on this side. And then on the other side you would have this, and like edges to between all of this, but n was 5,000. So you if you drew the solution, it would give you TLE because the idea would because it's n time n the number of nodes that we would have, n squared nodes times the number of edges that we have, n minus 1. It's probably also n squared, and with 5,000 it wouldn't pass.
But you have n nodes.
Okay, sorry. N squared edges. Yeah, okay, so n squared edges is the problem really. So yeah, sorry about the discount. So this wouldn't pass because the complexity of max flow min cost, if I'm not wrong, is n number of nodes squared times numbers of edges squared. So like a neat solution you could do to this is you could, instead of having an edge between everything, that's the problem we had. You could have an edge to only your neighbors. And the cost of that edge would be 1, because if you want to go to your neighbor, right, you would only have to pay a cost of 1. And the idea there is this edges could have infinite capacity because we don't care like how much anybody moves in general. And then you would have every one tied to like a source with capacity 1 cost 0, and every 0 tied to a sink with capacity 1 flow 0. And this way you would have like the ones try to look for an augmenting path to the sink, and they would pay the cost of going to the closest 0. So this can be solved with max flow min cost, and now our edges are in n squared, they are 2 per n, so there's n times, so it'd be n edges and I guess also n edges, and I think there might be like an optimization because everything has capacity 1. I'm not really sure about the complexity, but that gave accepted, like it passing time.
Okay, very good. Question, it's still a question here, hold on, she still has a question.
I was gonna ask you to draw again this
Okay.
graph so I can see it better.
Go draw the graph for her, but, well, I have a question for this. How many people did this problem? And is it clear that the original formulation, which was pretty simple, didn't work? Okay? There's no one who could have made that work, is there? Okay? So that's interesting to know. It's a question of, again, how tight the time bounds are, and I guess the memory bounds are on the problem, which would tell whether that's the case.
Was this the intended solution?
What?
Was this the intended solution?
No, this was from like an educational contest, and you had to do like either a DP or a greedy algorithm to solve it.
Yeah, because you need to solve this.
Yeah.
Okay. Wait, so greedy does solve this thing? Oh, no, never mind. Just,
Yeah, greedy also solves it.
right.
Smart greedy.
Okay.
We can continue on.
So they actually did flow directly, right? They run min cost max flow directly, right?
Yeah.
It looks like this is G, right?
Yeah.
So it looks like my team did a DP.
There's like no flow here, but I didn't do the problem. Like,
Yeah, it's because like the normal min cos max flow didn't pass, because if you did like just tripartite matching, it was too complex. But if you did like a trick of like only connecting it to your neighbors and having cost 1, then it does pass. Yeah.
Okay.
Okay. I don't know if you can see that better. I might be.
Should the outgoing edge be 0?
Okay.
Yeah. This go to 1s and this goes to 0. Oh, sorry. Yeah. You're done. Good. Yeah, the 0 go to the sink. So then it's like the 1 tries to go to 0 and goes to the sink. And then that's how you do like min cost max flow. That's why it works. Okay. The weights here are infinity between the edges, and the capacity here are 1. right? And one for each zero too. And then the cost of the edges here are 1. Because it takes like 1 to move from here to here. And like if this node wanted to move to like over here, it would pay 1, 2, 3. So yeah.
Why is the cost minus infinity?
No, it's infinity. Like, sorry, the capacity. The capacity is infinity.
Because we want like that you can move anywhere in the graph.
Okay, thank you. Okay. Okay, any other problems that people want discussed? I guess we have time probably for one more, if people really want it. What? H. Okay, H is buying sets. Did anybody, what? You want to, okay, so you're interested enough because you want to talk about it. Okay, that's fine. That is fine, by the way.
Someone wanted it. I wasn't.
That's the problem, like the last 10 minutes, I need to talk about it.
Okay, so, okay, go do your thing.
Okay,
Here,
so
take this. You can do
Okay,
that.
and this.
Okay, good.
Okay. Okay, so in the original problem, we had n sets. So, for example, I think the sample was like one set has like elements 1, 2, the other has 2, 3, the other has element 3, right? Those elements contains elements from 1 to n, and there are n sets, right? And aside from that, they give us a property about the collection of sets, where if you take a union between k sets, the union will be always a size at least k, right? And what we want to do is select some amount of sets. So maybe we'll take this, maybe we'll take all sets. Such that the union of all those sets has union exactly k. Right? So we want to take k sets so that the union is k. So for example, taking only those 2 sets does not work because the union has size 3 because we have elements 1, 2, and 3, right? So okay, so first observation, okay? This what?
The sets, they have prices.
What?
The sets, they have prices.
Yeah, I forgot about that. Yeah. If it was just unrelated, this problem would be like easy. We would just take no sets because like the union of 0 sets is 0 also always. But the sets have a cost to them, so I think the sample is like 10, 20, and the cost could be negative. So if the costs weren't negative, we also could just take no sets and we would have cost 0. But they also give the constraint that sets could have negative cost, right? So we will do the following formulation of the problem, okay? So we will make a bipartite graph with the elements and the sets. Okay? So maybe we have sets 1, 2, and 3. We have elements 1, 2, and 3. And we will say that there is an edge between an element and a set if and only if this element is in that set. So for example, in this graph, we would have something like this. Right? And now what we want to do is to find, okay. So the constraint that they give us at the statement is that for any k sets, we will have a union of more with size at least k. In this formulation, this is exactly Hall's theorem. That if we take a bipartite graph, and for any subset of k vertices, we can see at least k vertices, right? So for example, if we take those 2 vertices, we can see all of those 3 vertices, right? Hall's theorem says to us that if this is true, this graph has a perfect matching, right? So what we know from the statement is that this bipartite graph that they're giving us has a perfect matching, right? So, okay, how do we solve this problem now?
Okay, there's a question.
There's a question, okay.
What is the name of the theorem?
Hall's theorem. It's sometimes listed as Hall's marriage theorem.
Could you spell it, please?
Hall, okay, right, this I can spell.
H-A-L-L.
So, okay, so there is a very cool observation that helps us solve that problem. Okay.
Actually, so that's just a statement on certain graphs that have perfect matchings. Okay? Another way algorithmically you can tell if a graph has a perfect matching is to find it, use an algorithm. But this is a conditional, say that if the graph has this property, it has a perfect matching.
If for one side of the graph, if any subset of size k of one side of the graph, I don't know the name of that property in English, but like can see at least k vertices, there is a perfect matching. So for
Okay,
example,
if we're going to explain this, the way I think of it is this. Let's say we've got a bipartite graph. And suppose I tell you that I've got two vertices here. And if you look at all the outgoing edges, they only see one vertex. Okay? Does this graph have a perfect matching? Obviously not, right? These two people have to get married off. They only know one person to get married to. Somebody's going home alone, right? Hall's theorem is saying that if every subset on this side sees a bigger, at least as big a subset on the other side, which is necessary for there to be a perfect matching, in fact, there is a perfect matching. That's kind of what that is saying. Okay? And now I will retreat.
So in this visualization of the problem, let's think about what is a valid answer, right? So let's say that this, and also one simplification we're going to do to the problem. We know that there is a perfect matching, so we're going to relabel the vertices, the elements, in such a way that element I has a edge that connects with set I. Okay. So there is a perfect matching, so we could theoretically just find the perfect matching, construct it, and then we're going to relabel the elements such that element I has an edge to set I, right? So let's think about a valid answer. Okay, so we take a subset of the sets, and we know that there is exactly k elements in the union. Okay, so there's a perfect matching. So we know that the edges that are matched to those sets, the vertices that are matched to the sets, are in the union, right? So we know that the union is exactly this, right? Here is the important observation. Okay, if we have a valid answer, there's a bijection between every valid answer and a minimum vertex cover of this graph. Okay, so in this case we have this valid answer, this right here. Maybe another color. Those red circles are a minimum vertex cover. Okay? So why is that? Because there can't be any edge between those vertices and those vertices, right? Because if there was a vertex, there was an edge between those two vertices, this wouldn't be a valid answer because the union would also find these vertices and the union will be of size k plus 1 or more than k plus 1, right? So there are no edges between those three sets, right? And the minimum vertex cover has to be of size n because there's also this property that the size of the min vertex cover is exactly the same as the size of the bipartite matching, right? So if we have a bipartite matching of size n, we're also going to have a min vertex cover of size n, right? So the min vertex cover has to be of size n, and for every minimum vertex cover, we could just pick those elements, those sets that have a corresponding element in the vertex cover, right? So what we want to find now, does this reduction make sense? Okay. So what we want to find now is, what we want to find now is the minimum vertex cover such that the sum of the costs of the elements of that corresponding minimum vertex cover is minimum, right? Right. So the first thing I was thinking about is like trying to do some sort of min cost max flow. Like the max flow of, if we like make something like this, the max flow is gonna be n, right? Because if we have everything with the usual capacity, like capacity 1, and we would want to find the minimum cost of that, but it doesn't really work because like min cost max flow will not find the minimum cost of the min cut, right? So every vertex cover, every minimum vertex cover is also a min cut of the graph, right? But min cost max flow will not find as the minimum cost of finding that min cut. It will find the minimum cost of passing the flow from one side to the other, right? So min cost max flow doesn't work. So what is going to be the idea, okay? So initially what we could think about is, okay, so what if we just make a regular network without costs, only capacity, right? And we just put the weights of, so if this set has weight W1, we will make this edge has capacity W1. This W2, this W3, this W4, this W5, this W6, right? The problem, so for example, for this valid answer, this min cut right here would have the cost of choosing those elements, right? We will cut those edges, and we need to cut those edges to for this specific vertex cover. And this is exactly the cost of the set, right? Choosing those sets. The problem is we can't do that because we would have some edges with negative weight, right? With negative capacity. This can't work, right? So what we could do is, if, for example, this weight right here is negative, what you could do is, okay, so in a minimum vertex cover, in like an unweighted graph, we won't ever pick this vertex and this vertex, right? Because every edge in the perfect matching needs a vertex on it. And if we waste two vertices on the same edge in the perfect matching, we won't have a minimum vertex cover, right? So the problem will be the same if we just erase this right here and make it 0, if this is a negative weight, and put it here. Right? This way, we make sure that all weights are positive. And what we do is we're summing W2. We're actually subtracting W2 from those two edges to make it all positive. And we're gonna also make like n equals W2, because we're subtracting W2 from those two edges. So we're preemptively summing W2 on an answer. This formulation, if we just run min cut on this, will not find a valid answer, okay? Because what we're doing here is just weighted vertex cover. Weighted min vertex cover. what we want is a minimum vertex cover in the unweighted graph that that has the minimum cost, right? So we want the min cut of this graph to also be a min cut in an unweighted graph where all capacities are 1. So what we're going to do is we're going to sum infinite on our dose. So plus infinite, also sum plus infinite here. All those edges in the middle are going to be like infinite squared, you know? That way, any min cut of this graph will also be a min vertex cover in the original graph, and the min cut that it will find will also have minimum weight, right? Because it will first minimize the amount of infinites it takes, then it will minimize the cost of the edges it takes, right? So if we just run like Dinic on that, it's gonna find us like n times infinite plus actual answer. So we just subtract n times infinite. Does that make sense?
Okay, very good. Okay, thanks a lot. Give him a cheer, and let's move on. Okay, so today's thing. Let me clear this thing off. Just as a heads up, today's topic is going to be on something called combinatorial generation. The contest is not going to be specific to combinatorial generation. It'll be a broader range of problems, but this time. But I do find combinatorial generation is a very interesting subject, and it's one of these things that kind of are the way that I think about certain things. And so that's what I kind of want to teach in here. Do we have any physics people here? Some of you, I know we had some ORP. Is anybody majoring in physics? Okay, none of you. Do you guys ever feel physics envy? Like these guys know all this math that you guys don't know. They know about complex variables. They know about abstract algebra. They know about topology and tensor calculus and things like this. If you see one of these people and they're trying to make you feel bad, what I want you to go to say to them, if you follow my lecture today, is I'm a computer scientist, I can count, and I can do anything, okay? And I'm going to try to show you that you can do anything if you can count for some value of anything, okay? So let's not get too carried away. But what I'm going to talk about today is basically about what I think of as combinatorial objects, combinatorial structures, okay? And you guys have obviously used to working at with these things. I think of permutations, I think of subsets, I think of trees, and I think of strings, okay? These are things where there's typically a finite number of them once you fix the size, and for any n, there's a finite number of them. They often have some kind of nice properties, typically a nice recursive property, that there's a way to take one of these things and break them into a set of smaller things, okay? For example, if you have a permutation, if you take an element off of a permutation, like here we have a permutation 1, 5, 3, 2, 3. If I take the head off of it, what's left with the rest? Well, it's going to be an arrangement of, the original one had 5 numbers that were all unique. The second, when you take the head off, you've got 4 numbers which are all unique. And if you, let's say, consider a permutation as the numbers 1 through n, you relabel it, you can take the head off and you get a smaller permutation. With a subset, if you have a subset of things, if you take an element out of it, what do you have left? A subset. It's a recursive kind of thing. When you have a tree, if you take a node off of a tree, what do you have? A tree or maybe a forest of trees, things like that. If you have a graph and you remove some kind of an edge or maybe a cut or something, you've got another graph. So combinatorial things can be kind of decomposed into other things. And this is kind of what fuels a lot of the algorithms and things that we do here. Now, when you're dealing with, in combinatorics, you learn about a lot of objects, some of which I know are very simple to you guys, things like permutations and subsets you've seen lots of times in strings. There are more complicated combinatorial structures people know how to count. Things like set partitions and integer partitions and Young tableau, which I hope to talk about today. These are kind of more complicated objects, and trees and graphs, okay? So what I want to do today, again, when we talk about a combinatorial object, what do we know about them? For any number of things, okay, if you talk about any of these classes of objects, there is somehow an n that describes how big it is. Permutation, how many elements are in the permutation. A tree, how many nodes are in the tree. Okay? And for all of them, there is a finite number of things once you know what n is. Okay? Now, the number of objects for each, of different variants of each object typically grow exponentially, which means you can't list all of them for anything but a small number of items. You guys are used to, if I asked you guys to generate all permutations, how would you generate all permutations? Okay, if I said in a programming contest, print out the all permutations of 5. Yeah?
Next permutation.
Next permutation, and is that in a library or something like that? Okay, well, that's actually something to remember, because that's actually an important point of today's thing. But if you didn't, what would you do? If you had to do this from scratch, you would probably use backtracking, right? Now, but there are other ways of thinking about things, like the next permutation thing. What is the next permutation function doing? Okay? You could imagine a really dumb backtracking algorithm for next permutation. You start from the very, very beginning, list all the permutations till you get to the one you have, and then see what it generates next. That would be really dumb, right? But, and again, this is, you guys know about backtracking. I don't really need, so is there anybody here who's not familiar with, doesn't backtrack comfortably? I think all you guys know how to backtrack. Okay, we won't go through that. Okay, what are the things, the operations you can do on a combinatorial object? Once you define a class of combinatorial objects, I will say that there are several operations that are interesting. One that he says is interesting is next, okay, permutation. Next, if I give you an object X, give me which object appears next in the following order. Okay, there's an inverse version of that called previous. Give me an object, which is the one that appears before it in the order. Okay, but there are a couple of other ones that are also very interesting. One, of course, the simple one that's certainly true is just basic counting. How many objects are there of a particular size n? Then there's a pair of operations that are interesting, which I would say which are called rank and unrank. Okay? Rank takes an object and tells you where it is in the total order. So, if let's say you have an order of all permutations, how many permutations are there of n things? N factorial. If I give you a listing of them, each of them occupies a position in that listing from 1 to n factorial. Or if you want to be maybe a little nicer, you might say from 0 to n factorial minus 1. What if I now ask you, what is the 756,239,703rd permutation of 10 things? Okay? That is what ranking does. It gives you an object, and it tells you where is it in the order that you would get by listing them. Okay? So from ranking, you take an object and you get a number. Okay? Unranking is the inverse operation. It says, basically, given a number, give me the object that occupies that spot in the order. Okay? Does everybody kind of understand what rank and unrank mean? If you don't understand that, we're in trouble. So if there's clarification, I want that to know. Yes? Unrank is, I give you a number, what you call it? I give you a number, and you tell me what the object is that's at that position in the order. Okay? So, okay. Here's a joke that is maybe relevant to this, and maybe won't convey. If so, I'll back away. There's this talk of all these prisoners, okay, that have been, they're in jail together for they're serving life terms. They've been there for 10 years, 20 years. To keep themselves entertained, they tell each other jokes, okay? And of course, they don't know any more jokes because they've been in prison all the time. So what they do to save time, they tell each other the number of the joke, okay? And so they have an idea that if I say 672, okay, that they know that maps to a joke, right? And so new prisoner comes to jail. He's now his first day in prison. He's sitting with the prisoners and they're going to each other. One of the prisoners says, 593. Everyone starts laughing. Someone else says, 492. So the new prisoner wants to prove he's cool. So he says, 123. Dead silence, okay? And someone says, all other prisoners shake their head and they say, that guy doesn't know how to tell a joke, okay? Now, what is going on in that joke? In some sense, there is a mapping the prisoners have between numbers. It wasn't a completely random thing I took you on, right? The prisoners have a listing of the jokes in their head, right? From 1 to n. There's a canonical set of jokes, okay? If you give a number, all the other prisoners, okay, know what joke that is. Unranking the joke is reconstructing what the joke is, why they should laugh, in some sense, from the number, okay? So let me go back to that again. Now let's say it again in math. Rank says, if I have these objects in an order, rank tells me what is the position of this object in that order. Unrank says, if I give you a number, tell me what object is at that position. Okay? Any questions about rank and unrank? Okay? And there's one other object operation I haven't talked about here, which is random generation. One might say, given n, give me one of the objects uniformly at random. Okay, I'm sure that in your life you have, at some point in your life, wanted to construct a random permutation. Is there anyone here who's ever wanted to construct a random permutation? Okay, I see some people nodding. You know, those of you who know about that kind of thing have some slick algorithm in mind that you're doing with it. But you'd like to be able to give me every one of the n factorial permutations with equal probability. I want one permutation. I want all of them you to pick one with equal probability over the space of entire permutations. So these are the basic operations on combinatorial objects. Any questions about that? Okay. So these are, I guess, just examples. Maybe this would have made it easier than the joke. Okay. Here are permutations. There are 6 permutations of 3 things. Okay. They are in a particular order. The order I have them written from left to right. Count of 3 is 6 because there are 3 factorial permutations, and 3 factorial is equal to 6. Rank of 1, 2, 3 is, according to this, 0, 1. Rank of this is 1. Unranked said, what's the third one out of all permutations of 3? 0, 1, 2, 3. It's 2, 3, 1. Next, what's next? That's the one that he liked over there. Next for a permutation, next of 2, 3, 1 is going to be the one right after it in the order, which is 3, 1, 2. Previous is the opposite way. What's the previous permutation for 1, 2, 3? This maybe is a little bit interesting. Okay? You could say it's at the beginning of the list, and so I don't give you anything. Or you could say it's the one that's at the end of the list. You kind of think of them as a circular group of permutations, which is kind of what I like. Okay? So next and previous, you shouldn't be able to fall off the end, is what I want to say. So previous of 1 through 3 is going to be 3 through 1. Okay? And random generation is I pick one of these with equal probability. I picked 1 through 3. Why did I get 1 through 3 as my random permutation? Just the way luck worked out. If we show the slide again, it'll have a different thing on it. Okay? Any questions about that? Okay, so people understand the basic operations. What are the properties of these functions? Let's now think about this kind of, these operations as some abstract thing. First, what happens if we have an object X, we rank it, and then we unrank it? What do we get happen? When we rank it, we get its number in line. Okay? When we unrank it, what do we get? We get the original object back. Does everybody agree with that? This is a good way, by the way, if you want to test your rank and unrank functions. A great thing to do is to run it through either a bunch of random examples or all the examples. Make sure that that holds. Okay? He did next, he wanted to know how to do next, he didn't want to know, he wanted to call next permutation. How can we get a next permutation algorithm? Well, what if I take your permutation X and I rank it? Rank it, I now get a number. That number is 56. What is the permutation after 56? It is the permutation, yeah? 57. Okay, so if I rank it, I get a number. If I add 1 to it, I get the next number. And if I unrank that, then I get the next permutation. This is what might be going on in that, not necessarily what's going on, but might be what's going on inside the next permutation operation he talked about. Okay? Previous is obviously the, actually previous would be the same thing with a -1 here, but I made a typo, right? But previous, it should be a -1 there and not a +1 there. Okay? How do you randomly generate things with equal probability? If I ask you to generate a tree, a labeled tree on n nodes at random, that feels like a non-trivial problem. But if I know how to rank and unrank and do these other things, okay, I claim all I have to do, if I know how many items, how many objects there are, which is count, I know that my ranking values will go between 0 and count -1. If I pick a random integer uniformly from 0 to n-1, and I unrank this, I get a random object. Okay, does everybody kind of get that idea? Okay, so this is good. Okay, and so it's clear that there are relations between all of these operations. Okay, if you have a system for doing this. Okay? Now, okay, let's just keep going. Now, when we do this ranking or unranking, okay, we have to do it with respect to an order of the operations. This gentleman was busy calling next permutation. What does next permutation mean? How many different orderings of n of all permutations of n are there? Let's think about it. If I have if I want to know how many orderings there are of n, of the permutations of n things, how many orderings are there? N factorial, factorial, okay? So there's a lot of different possible orderings that you could have, okay? But I'm going to claim that 2 of them are typically most natural and tend to come up a lot. There's other natural ones, but one of them is lexicographic order, which would be what were the order that they were sorted in, okay? And for permutations, if 1 is less than 2, less than 3, all the permutations starting with 1 appear before all the permutations starting with 2, before all the permutations starting with 3. For subsets, okay, again, you might think about it, again, there's different, when you think about it, sorting it lexicographically, typically the empty subset is before, and we'll sort them based on the first item that they have. If they have 1s, all the ones that have 1s go before anything that doesn't have a 1. Of the 1s then, the ones that then have 2s go before the ones that don't have a 2. So, sorting them looks like that, okay, for subsets. It's a little bit of a weird order, actually, okay? Minimum change order is another order that is interesting, which is, can you find an arrangement of these objects which change as little as possible as you move from one to the other? Let's look at the minimum change order for permutations. What's the smallest difference you can possibly have between 2 permutations of n? Can you have one item in a different position and all the others be the same? No, because they're the same set of items. You can have a swap between 2 items. That's the smallest change you can make between 2 permutations. And in this minimum change order, there's exactly 1 swap of things. What happened from here to here? What did I swap? I swapped 1 and 3. Okay, good. You guys are going to have to help me here. What did I swap from here to here? 2 and 3. Here I swapped what? 1 and 2. Here I swapped what? 3 and 1. What do I swap here? I guess 2 and 3, right? And what do I swap going back? To get from 2, 1, 3 to 1, 2, 3, I swap the 1 and 2. Does everybody see that's an order of minimum change? And it's a cyclic order. Okay, it doesn't end at the end. Okay? Now, with permutations, you could get even fancier, actually. There's actually ways of generating permutations where they swap. Not only is there an ordering where they swap one element pair, but that pair is always next to each other. Okay? So you can do that. For subsets, what's the smallest change? The smallest change is, in this case, 1 insertion or a deletion. Here we go from this. We insert a 1. We insert a 2. We delete the 1. We insert a 3. We insert a 1. We delete a 2. We delete a 1. We delete a 3. Okay? So if you have any set of operations for doing rank and unrank and all this kind of stuff, it's with respect to a particular order. That's kind of got to be clear. Okay? Any questions about that? Okay. So what do I now want to do? The rest of my time I'm going to talk, assuming I get my act together, keep my act together. We're just going to go through one by one for a given set of objects. How do you rank it and unrank it? Okay? In ways that are kind of interesting. Okay? And let's start with subsets, which are kind of a simple thing. Okay? First thing you need to do is to count. Okay? How many subsets of n things are there? 2 to the n. Why is it 2 to the n? Okay, there are a couple of, simple things. One is simply the recurrence, that if you have on account n things, okay, either it includes the nth element, the subset, or it doesn't. So the number of subsets of n things is 2 times the number of subsets of n minus 1 things. Once you've got a recursive formula, you can count, okay? And now you guys know how to count. You already knew how to count subsets. That much I know. Now, if I ask you to generate subsets, okay, I think I know what your favorite order or way to generate subsets is. It's probably by just having a loop that goes from 1 to 2 to the n, and counts the binary representation of that, okay? And now you know that if you're representing a number n, okay, if you're representing a number with n bits, it can have a value from 0 to 2 to the n minus 1, okay? Every bit that means that there's as many bit patterns as there are subsets. You're also, and that in some sense gives you a natural ranking order for subsets, right? Your favorite order was binary counting. Now, my question is kind of this, before we take a look at this, just to think about it, because I think you can derive this pretty readily. Now, if we're going to generate subsets in that order, what is that order? I guess it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. This is all counting here. Boom. If we generate it like this, how do you do ranking and unranking? It should be clear to me, if I give you a subset 1, 3, how would you come up with the ranking for where this subset 1, 3 is? What's the number of that subset in this order of all subsets of size 3? Okay, this is obvious. This is what you're telling me is, this is going to be the bit pattern 0, 1, 0, 0, 1, 0, 1, okay? That is the Boolean number 5, that is the binary number for 5, right? It should be clear that you can do ranking from, given the, the subset, come to the binary representation. From the binary representation, treat that as an integer. Now I have a rank for it. How do I unrank this, a number, something? Now I give you a number 7. What is the subset that corresponds to 7? This is now the unranking task. First you write it in binary, and this one seems pretty clear, right? And now you interpret it as being 1, any element 1, 2, 3. This is going to be the 7th one. Okay, so we know, I think, how to rank and unrank subsets. And if we don't, I'd like some questions here. I see some confusion. Yes?
Is 1, 0, 1.
Okay, so what is this subset? So first of all, in order to do this, we need to know what n is in advance. So notice that somehow there's a magical n equals, not a magical, an implicit n equals 3 here. Notice that where this was ranked or unranked would be different if we had a different value of n. N is the size of our set, right? So what are we going to say here? We're going to represent, because of there's this bijection between binary strings and subsets, where we say that a bit is, the ith bit is 1, means that element I is in the subset. That's why we say for 1, 3. Okay, we know that because n equals 3, there's only 3 slots. 1 is the first item. The fact that it's there means that's got to be a 1. I don't see 2. That's got to be, is it not there? 3, that's 1 there. Okay, do you see it or not? Okay, because I still, okay, hopefully that does it. Okay, any questions about that? So, what do we know now? We can, in fact, ranking the subsets in lexicographic order turns out to be a difficult task, but for this binary thing, this is trivial. Now, everybody sees. We know how to count, we can rank, we can do all these kinds of things now. So for subsets, this is now easy, I will proclaim. Any questions? Okay, now, there is another way, though, to think about ranking and unranking these subsets, which is, is there a way that I can do it without explicitly constructing this thing? I'm going to claim that if I know that n is this, there is a difference between, what do I know is the difference between things that are above 2 to the n minus 1 and below, this is sort of the cutoff of 2 to the n minus 1. What do I know? If the number is greater than 2 to the n minus 1, that means that it has the first bit set high, right? So any number that is set greater than 2 to the n minus 1 has to have element 1. And if we now take let's say we want to unrank this number, okay, what do we know? We know that this number is greater than 2 to the n minus 1, so it's got to have element 1 in that subset. But if we now take this number x and subtract, make it x minus 2 to the n minus 1, does everybody see I've kind of masked off the first bit? I've got a smaller number that is now between 0 and 2 to the n minus 1. 2 to the n is equal to 2 to the n minus 1 plus 2 to the n minus 1, right? If it's above here, I now have a smaller, if I subtract that thing off, I've got a smaller number of bits left and a smaller integer. And so I can do this unranking in a recursive way. Does everybody kind of see that? And the key thing here is not, oh, look at the magic, it's a binary thing, I know one bit maps to another. What am I doing here? I am reducing the task of unranking to counting, okay? When the number, if I knew that there were n items, and I knew they were listed in this order, what am I going to do? I am going to subtract off reconstruct part of my structure, subtract off the number, and I'm going to have a smaller problem to solve recursively. And this is the way I generally want to solve my ranking and unranking problems, okay, is by reducing them to counting. Any questions like that? Okay? We'll see some more examples of this, but this is kind of the way I really kind of want to do it. Okay? Any questions? Okay? One other thing that I think many of you know about, but it is almost a digression from this, but it's an interesting digression. One thing about subsets is that they can be generated in a minimum change order. Okay? Minimum change order, remember, meant they inserted one element or deleted one element as you went from one to the other. Those things are called gray codes. Okay? And they're kind of interesting things. How many people know about gray codes? How many people don't know about gray codes? Okay? Fair enough. There's a way to think about minimum change ordering, which I find kind of a productive way to think about it, is as a Hamiltonian cycle on a graph. Okay? What do we know about graphs? Graphs, vertices and edges, you know about graphs. If we think about if you have a graph where the vertices are your combinatorial objects, and you have an edge between any two objects that differ by a minimal amount, that's what we will call an adjacency graph for this object, right? Let's think about it for permutations. Suppose I give you a a permutation of size n. This is an n-element permutation. What's the minimum change to another permutation? One swap. How many permutations are one swap away from this permutation? N choose 2, because any pair of positions can swap. Right? Does everybody agree with that? So implicitly in the world of permutations, there is a graph out there with n factorial vertices where every vertex is connected to n choose 2 other vertices. And if you have a graph like that, if you want a cyclic order to generate all permutations with the minimum amount of change, what's the right way to think about that? Find me a Hamiltonian cycle, a tour that visits every vertex without hitting vertex more than once, okay? That will be such an order, okay? Does everybody kind of get that idea? If you have a graph where there's an edge between every permutation and any other one that is a minimum change, then if you find an order that visits all the vertices, okay, you got it. The graphs that you get from looking, yeah.
I can't see why it's n chooses 2.
What?
I can't see why it's n chooses 2.
Well, let's just think about it.
I thought you were supposed to turn on a 0 or turn off a 1.
Oh, I'm talking about permutations, not subsets here.
Okay.
So here I'm talking about
Permutations. 1, 2, 3, 4, 5. How many permutations are within one swap of this? Okay, for subsets, that's a good question, though. How many if we look at the subset graph now, if I have a n-element set, how many, and I give you a particular subset of it, let's say governed by some binary string, how many string subsets are within one addition or deletion of this subset? Now it's n. I just have n bits. I flip any one of them. I get to the nearest neighbor, right? For subsets, you're right. There's going to be, if we have n, a world where there are n-element subsets, subsets of an n-element set. They are represented, each subset is a binary string on n elements. Okay, there are 2 to the n of them. Each one of these is adjacent to n other ones. The structure of that graph turns out to be very interesting. The structure of that graph turns out to be a hypercube. Okay? What is a hypercube? A cube in 2 dimensions is just a square. A hypercube is 2 cubes of the lower dimension. Okay? And we add an edge between the corresponding vertices. And so here, every time, every vertex is a string. We had a hypercube first of 1 dimension, then 2, then we doubled it again, we got 3. In general, for an n-element thing, there is a hypercube graph where any Hamiltonian cycle on this is going to be an order where there is a minimum change as you go from one subset to the other. Any questions about that? Okay, these graphs are often kind of interesting. There is a very slick way to generate subsets in order of minimum change, which is a recursive thing which I just want to quickly show you. Suppose you have a subsets here of the 4 subsets of 2 things listed in minimum change. 0, 1, add a bit, subtract a bit, subtract a bit. If I make 2 copies of this, this order, and I put it next to a reversed copy of itself, what is going to be the adjacencies here? This to this is going to differ by 1 bit, 1 bit, 1 bit, 1 bit, 1 bit, 1 bit. At the border, there's going to be a difference of 0 bits. If I now append the top half by a 0 bit and the bottom half by a 1 bit, there is no change in the distance between the strings in either half. There is a distance in the one at the boundary now differs by 1 bit. This order gives you a gray code. Maybe it's not, either you've seen that before, or if not, it's kind of a cool thing. Any questions? Okay, but let's get back to where we were. We want to do ranking and unranking, okay? How do we rank and unrank strings? Okay, if we have an alphabet of size n, of alpha, what is the number of strings of length n on an alphabet of size alpha? How many strings are there? Okay, we have alpha to the n, right? So I have an alphabet of size alpha. Okay, if I have n string, n positions here, there's alpha choices for this, alpha choices for that. It's alpha to the n is how you count them. How can we rank the strings? Here, if you look at this thing, here I've got all the strings in what you call it, in lexicographic order on the alphabet 0, 1, 2. Okay? How can I rank a string from 0? Do you see what I now have my problem? I want to now rank strings generated from an alphabet here of size 3 of length n. What is going to be the position of the string 1, 2, 2? Okay? How can we figure out the ranked position of a string, okay, in the lexicographic order? Yes?
Think of the string as a number written in base 3.
Okay, you want to think of it as a number in base 3? That may be a way to think about it. And actually may even be the same way that I'm going to think about it. But I'm going to think about it the way I think about it, okay? What do I know about a string of base 3? Okay, no, a string on my alphabet of size 3. If I have them in sorted order, what is it going to look like in sorted order? We agree that there's going to be a bunch of strings that start with 1, then a bunch of strings that start with 2, and a bunch of strings that start with 3, right? How would I figure out what is the ranking of 1, 2, 2? Let's make it maybe more interesting. Let's make it 2, 1, 3. 2, 1, 2, fine. Okay? What do we know? What is going to be the ranking position, the number of this string in sorted order? How would we figure this out? Okay? I claim that because it's recursive, we have a first character, and when we take it off, we're going to have smaller strings, right? But what I know about the strings of size 2 is that any string that begins with a 2 is going to be after the strings of size 1, right? How many strings are there going to be of size 1 of length n?
-1.
Okay, it's going to be alpha to the n minus 1. This chunk is going to be of size alpha to the n minus 1, alpha to the n minus 1, alpha to the n minus 1. Does everybody kind of see this? Okay. Now, how do I rank this string? Well, what do I know? If the first character is 2, that meant that it is after the first chunk, right? If in fact the first character was 3, what do I know? It was after the second chunk. So what is the rank of this going to be? I claim it is going to be the rank if the first character is C. What do I know about the ranking of this? It's going to start off being C times the number of strings of length 1 less than that. It's going to be C minus 1 times alpha to the n minus 1. Do people see this? Okay. Now I know if it started with a 3, if I subtract this off, this is the position of the first string of length 3. And now, once I chop the first string with the head of 3, once I delete this, what do I now have? I now have a ranking problem where I've got n minus 1 characters. I still have an alpha, okay? And I now know that what is the ranking of the string 3, 2, 1, 2? It's going to be this plus the ranking of the the substring 1, 2 on an alphabet of size 3. Okay? Do people see what I'm doing here? I claim that there is a recursive way now to come up and rank what that string is. Okay? How many people see this, what I'm doing? How many people don't see it?
How many people have lost interest at this point? Okay, a few, but that's okay. What is interesting here? Do you see now how I can build this recursive function to rank, and by taking the inverse of it, unrank these strings? Okay? How would I unrank a string? Suppose I ask you, in the case of, let's just look at my example here. Suppose I ask for the 26th, I want to unrank. What is the 26th, string of length 3 on an alphabet of size 3? What do I know? 26. If I compare it to what is the size of strings of length 1 less than that, there are 3 to the 2 strings in each block. What do I know about the 26th string? It can't be in the first block, it can't be in the second block, it's got to be in the third block. And so I can peel off the first symbol of this has to be a 3, and I can solve it recursively. Any questions about that? Okay, so you should be able to work out the ranking and unranking functions for strings, and it should be clear that they follow directly from the ability to count. Okay, that's what's driving this thing. If we know how to count, we can figure out to rank and unrank things. Any questions about that? Okay. Let me show you one other cute thing, and then I think I'll let you break, okay? But this is a cute thing, okay? Maybe take a little time for a cute thing. What if you wanted to have a string? We said that, what if we wanted the shortest string that contains all strings of length k, okay? Let's go back a little bit. Remember last lecture, I was talking about suffix trees. And when I talked about suffix trees, at one point I said, what is the string that would generate the biggest uncompressed suffix tree? Do people remember that when we were talking about that? What string would generate the biggest uncompressed suffix tree? Does anyone remember? We talked about random. But random isn't exactly the one that would generate the biggest uncompressed suffix tree. What?
Of the characters different.
If all the characters were different, if you said you had a string where all the characters were different,
that's great, but that's an infinitely large alphabet. You don't live in a world where I don't speak a language with a large alphabet.
if I wanted to build a string that had the worst possible uncompressed suffix string, what would it look like?
Lot of A,
What? What?
a lot of A's, for example, and a B at the end.
If I had a string that was all A's with a B at the end, that would be a tree that, no, that would not look that would look something like this. That has very few edges. What would be the tree that looks like it has the most edges? Okay. What?
We want to have like very different patterns.
You want very different patterns at the beginning, right? What would be the maximally different patterns that you could have? What if you had a string that had all possible patterns? Okay? What would be a string like that would be all possible patterns? Okay? It would be a string with the property that looked something like this. Look at that string up there. This is on a binary alphabet. If we look at all strings of length 3, 0, 0, 1, 0, 0, 0 appears there. If I slide over by one more, okay, you see how I get another pattern of size 3, string of size 3. How many strings are there if I have an alphabet of size alpha and a length of size k? How many strings were there again of that size? Alpha to the k. If I wanted to represent all alpha to the k strings of length k, how long a string do I need to do this? Okay? Okay, the dumbest way to do it would be to concatenate them, right? I could list all alpha to the k strings and just concatenate them, and that would then be of length k alpha to the k. Okay? But if I could do it better, I could arrange all the patterns so they overlap each other. Does everybody kind of see that? So a De Bruijn sequence here is a string with the property that it is the shortest string that contains all alpha to the k strings as substrings. Okay? What's the minimum length I need to have? I need to have the length of this string has to be shorter than, can't be shorter in some sense than the number of different strings. Well, let's just look at the one we have here. I said 0, 0, 0, 1, 0, 1, 1. I think I have one more 1, right? Basically, I'm going to represent every string here. And then this wraps around. So there's one that goes here, one that goes here. Does everybody see that this string has all of the different substrings if we think of this as a circular string? Okay? This is what we would have wanted to make for a bad suffix string and is a useful thing to be able to think about. Okay? So how do we construct a short string that contains all possible patterns? Okay? How many people have seen this before? A few? How many haven't? Okay? Okay? Now this is an interesting thing. This is a thing that, suppose, let's say you were a safe cracker and you wanted to open a safe and the safe remembered the last few numbers that you had done, right? So it didn't require you to start from scratch every time. This is exactly the sequence you want to enter. Okay? So any questions about what this, okay, I'm getting coffee here. You get a choice. Do you want to see how to do this now or do it after coffee? Who here says now? Okay, who says after coffee? Okay, good. Okay, you're dedicated enough, I'm going to do it now. Okay, that was the vote. What if we build a graph with the property that every one of our substrings, okay, we have here. Let's look at this particular graph. You could think of it as, by using our adjacency idea, What if I build a graph where the vertices are going to be my strings of length k, and I'm going to add an edge between every string of length k and a directed edge from this string to this string, if there is a way to make this string by sliding this thing over 1, deleting the first character, and adding another character. Notice you can go from a 1, 1, 1 to a 1, 1, 0 by sliding it over, taking off the first character, and adding a 0, right? You could go to make a 1, 1, 0 into a 1, 0, 1 by sliding it over and adding a 1. So I claim we have a directed graph here where every vertex is our pattern of length k, okay? It's directed and it tells you how to, it's a directed graph and the edges are labeled like this. If we get a graph like this, how do we find a string of minimum length that has the, reconstructs every one of these strings? A Hamiltonian cycle in this graph. Does everyone remember? That's the same trick we did with the gray codes, right? If we had a graph like this, if we find a cycle that visits every vertex, the pattern of zeros and ones we get, okay, defines our string. How many people see that? Okay? I want you to think about it. See the basic idea? We have every object, we have an adjacency, we connect them. A Hamiltonian cycle will do that. Okay? What's bad about a Hamiltonian cycle, though? Hard to find one, right? There's a cleverer way of doing this. What if now we build a graph? Now this was for k equals 3. Let's take that exact graph for k equals 3 and use it to now find every string of length 4 that, build a string that contains every substring of length 4. What do I know? When I move from here to here, I move from 1, 1, 1 to this node. I added a 0. Does everybody think, can you think of this edge as being the string 1, 1, 1, 0? That's now a string of length 4, right? What is this edge going to be worth? This is going to be 1, 1, 0, 1. Does everybody agree every edge here is now a string of length k plus 1? Is it possible to find a tour that visits every single edge in a graph? What do we call that? An Eulerian tour, right? Is it hard to find an Eulerian tour of a graph? No. So now what is the interesting trick? If you want to build a string where you have every pattern of length k, build a graph where you have every vertex is a string of length k minus 1. Add these edges linking these things. And then every edge, think about how many edges are there going to be going out of a vertex. It's how many ways, it depends upon the alphabet size, right? So there are, if there are alpha to the n of the vertices, there's alpha to the n minus 1, n plus 1 edges, right? So what's cool here? If I find an Eulerian tour of this graph, then it will give me a string that generates all patterns of length k plus 1. How many people see that? Okay, a few people. Okay, this is kind of cool. Okay, any questions? Okay, there's no questions at this point. You can have coffee, but you can look at this and figure this out because this is kind of cool. Okay, thank you.
Teste, teste.
Só testando o microfone, galera. E aí?
Ah, então não tá hoje, chama. Ah, bem capaz, né?
Teste de som, 2, teste de som, 2, 3, 4.
But
it again. Okay. In the previous session, I was showing you, we got distracted by a couple of cool things like de Broglie sequences and graph sequence, actually, and Gray codes. But the basic question we were still looking at was how do you rank and unrank objects? And just to make sure, there's a lot of interesting objects I want to talk about. Just to make sure that people understood what we were doing, how would we rank and unrank permutations? Remember, if I wanted, that was the question he had wanted to do next permutation earlier. How do I rank, how do I take a permutation and map it to a number from 1 to n factorial? The basic idea was I know how to count how many permutations there are of n things. If you give me a number, it's going to be between 0 and n minus 1 factorial. What is the first number in a permutation? If I give you, I want to know the billionth permutation of size on n items. Well, if I'm listing the permutations where the first thing is 1, all of those permutations appear before all the ones with 2, 3, 4. Do this recursively. Then what do I know? If I have my number x, I find what is the multiple of n minus 1 factorial, the biggest one that's less than x, okay? That will tell me which bank of permutations I'm in. I am then going to, once I know where my value x sits, okay, in this thing, that will tell me, depending upon what the multiple of n minus 1 factorial is, it will tell me the first item in my permutation. I can print that out, subtract this bound, which was 1, 2, 3 times n minus 1 factorial off from x, and now I recursively have a smaller number, and I have a permutation of length shorter than that. And by doing this recursively, I can rank and unrank permutations. How many people understand that scheme well enough that they could probably reproduce this or something like this if they had to? I think most of you do, okay? So instead of talking about permutations further, I would like to talk about a some more esoteric combinatorial objects that are still important, but that you will not maybe have seen as much of. And one of them is integer partitions, okay? Integer partitions are ways of breaking a number up into small integers, positive integers, such that it adds up to n. So if we take a look at what is an integer partition of, let's say, 6, it's a multiset of integers that adds up to 6, okay? 6 adds up to 6. 5 plus 1 adds up to 6. There's no other thing that of positive integers with a 5 that adds up to 6. With a 4, 4 plus 2 adds up to 6. 4 plus 1 adds up to 6. Does everybody kind of get that idea? I claim this is a complete enumeration of all the ways you can make up 6 by adding up numbers where the order doesn't matter, okay? And a set of numbers that adds up to n, okay, is called an integer partition of n, okay? And for convenience, we will typically represent the pieces in sorted order from smallest to biggest, okay? Any questions about what an integer partition is? Okay? These things are objects. We would like to do with them like we do with every other object. Okay? We'd like to be able to rank them and unrank them. Tell you what is the 96th partition of 102. That's a well-defined question. Okay? And that's the kind of thing we'd like to be able to do. To do that, we need an order on the partitions. Okay? And typically, this kind of lexicographic order is the one that I'm going to use. Okay? where we have them sorted by what is the biggest part, okay? You like that better? Okay, however you like it is fine, okay? We have the partitions sorted by what their biggest part is, okay? And if you do this, then in kind of, I guess this is a reverse lexicographic order, okay, is the natural way to represent all integer partitions. Any questions about what an integer partition is? Okay? And certain things in life, okay, are integer partitions. One thing that me as a research professor am very concerned with, my favorite integer partition in the world, has to do with how often my papers have been cited, okay? So what do you know? If you're a professor, what do you do as a researcher? You write books and papers. How do you tell if a paper is good or not? Okay? Okay, well, if other people read the paper and do something with it, that is good. That's a measure of how good it is. So if you look at something like Google Scholar, how many of you are familiar with Google Scholar? Okay, this is a great way to look up research papers. Okay? For every professor, you can look at all the papers that they wrote, okay? And they have them sorted by how many times they were cited, okay? And what you call it? If you can think about all the papers I've ever written, every row of this partition represents one of my papers, okay? And the columns here represent how many times somebody cited my paper in something that they wrote, right? So what do we know? What's the first row? The first row here of dots here is my most heavily cited paper, right? And the number of dots is how many other papers that cited it. So when you look at a professor's record, you can describe it by an integer partition like this. Does everybody kind of see that? It's a partition of the total number of citations I have had. Okay? Any questions? And there's another, one of the measures they use to say how good a researcher somebody is, or somehow, you know, how much their papers are cited, is something called their H index. Okay? What is my H index? My H index is, H is the value such that I've had at least H papers which have each had at least H citations, right? If I wrote 10 papers that each had 10 or more citations, my H index is 10, okay? And what is the interpretation of someone? My H index is 66, so I'm good, okay? But not as good as people who have higher H indexes, okay? What is the interpretation of someone's H index in their integer partition of their citations? I claim it's that red square. Okay, what is the red square? We took all the papers, we sorted them from most citations to least citations. Okay? My H index means is the biggest square you can put in this drawing, showing that I've had at least, at that point, at least, in this case, H papers, that's the columns, each of which has received at least H citations. Any questions about how we draw pictures of partitions and what this thing kind of means? Okay, so there are a lot of things in the world that are citation, that are permutation, that are integer partitions. Okay, and they're interesting things to think about. Any questions? Okay, the first question is, how many integer partitions are there? We've said that if we know how to count something, we can do all kinds of things, okay? How many integer partitions are there on n things? The way that I would count that is I would instead try to develop a recurrence that says, gives the count as a function of n where the largest part is at most k. So if p of n k
is going to be equal to the number of partitions, integer partitions, of n with largest part less than or equal to k, right? How do we count this? How many integer partitions are there of n whose largest part is of size k or less? Okay? Can anyone give me a recursive formula for this? Again, you're supposed to be computer scientists. You're supposed to know how to count, right? Okay, how many ways are there?
So perhaps we could say, consider the partitions that have largest element exactly k.
Right.
Be p of n minus k and k.
P of n minus k, okay,
And k.
means what? So what does this mean? What does this count?
That means that the first element, the largest element, is
The
exactly
largest
k.
element was exactly k. How many partitions are there whose largest element is exactly k?
So the remaining will be
Well, if there is one, if you take that largest element out, you've got k, you've got a n minus k stuff left to add up, and you're still allowed to use parts of size greater than k. Does this count all the partitions of size k? No. What are the others?
so we're missing the ones that don't have
We're missing the ones that don't have a piece of size k, right? How many of them are there?
p of n k minus 1.
Okay, does everybody see this? Okay, any integer partition either has a part that whose largest part is less than or equal to k, either has a part of size k, or it doesn't have a part of size k. This is counting the ones which do have a part of size k. This is counting the ones that don't have a part of size k. Okay, any questions about that? So we can count integer partitions, right? If we can count them, can we do anything else with them? Okay, well, that's a trick. I'll tell you, maybe ask for the trick afterwards. How do we rank and unrank these things? Well, if we can count them, we should be able to come up with a way of ordering them. What is a natural order for the right order for our partitions to be? They're going to be, first, the number of parts. If, let's say, we wanted to come up with all partitions of length n, let's first use the ones which have largest part k, largest part n. Then the number of partitions that have largest part n minus 1, n minus 2, till the largest part was equal to 1. How many partitions have the largest part n? 1, just n. How many integer partitions of n have largest part 1? 1, just 1 plus 1 plus 1 plus 1. Okay, n times, right? In general, for different values of k, okay, this is the ones that say what the actual largest part is. How many partitions are there of n with exactly, largest part exactly k? Okay, if we want to know how many partitions there are with exactly largest part k, that's going to be p of n k minus p of n k minus 1, right? Because this says all the things that have parts great. These are all the ones that have parts, largest part k less than or equal to k, minus all the ones with largest part k minus 1 or less. That's going to leave the ones with largest part k. So how do we rank or unrank these things? Suppose I want to know what the 96,702nd integer partition of 6 is. How do I tell? I ask myself, if my number is here in sorted order, what do I know? Okay, these were the number of they started out with all the partitions that were largest with n. Largest part n minus 1. The sum of how many of these there are before this will tell me, it gives me a way to tell what the, for any particular x, what the largest part in it is. Let me say that one more time. It should be clear, ultimately, this is not that hard what I'm about to say. I'm probably going to stumble over it. But what is the idea? If I want to know what the x integer partition is in this particular order, what do? If I tabulate what the largest number of partitions of size n are, n minus 1, n minus 2, n minus ... If I keep a running sum of this thing, number of partitions of biggest part n, biggest part n or n minus 1, n minus 1 or 2, if I keep a running sum of this, it's clear that what is the largest part in the x largest partition, the x, the rank x partition, it's going to be what is the place where the sum of these counts, is where's the place where the sum of this first becomes greater than x? That will tell us what the largest part in this partition is, and then we can subtract off the count up to here. We're working with a smaller integer, and we can recur, How many people understand now how you would go and rank partitions? How many people don't see it? Don't see it? Let me try to say this one more time. What is our basic paradigm here? We are trying to figure out what is the x largest partition in our order. Our order is generated according to the size of the largest part. We know how many integers there are of each largest part. If I am given x, what is going to be the largest part in x? If I sum up the number of partitions with largest part n, this range from 0 to the number of partitions with largest part n minus 1. So this is actually going to be 1. But in general, what do I know? My permanent partitions appear in a block. I know the number of partitions in each block. Each block has the same largest part. The prefix sums of this thing give me, what is the largest, what is the rank of what is the range of ranks in the total order of partitions, whose largest part was n minus 2. When I compare x, I compare it to this prefix sums. The largest prefix sum less than x defines the start of the block that contains my number. Once I do that, what can I do? I subtract off these numbers of partitions, from my x. I know my largest part is n minus 2, and how do I recur on it now? I recur on the problem where I have n minus, originally I had n, my largest part here was, if it was n minus 2, n minus 2, the remaining stuff I have to put in my partition is going to be 2, and my largest part, has to be less than or equal to n minus 1, n minus 2. So I now can recur and keep pulling off my largest part successively. Okay, and this gives me a way to rank what, to give it a number, unrank it, or by doing this in the opposite order, given a partition, to rank it. Any questions about that? Okay, so this I think is now a kind of a cool thing. Okay, even though integer partitions seem very complicated, it's easy to build next, previous, random, select them at random, once you can establish this kind of bijection with the integers. Any questions? Okay. What other things are interesting with partitions? Again, if you think about integer partitions, there are a lot of cool things about integer partitions that you can see kind of when you look at the diagram. What is the relationship between the number of partitions? Here we were counting the number of partitions with largest part k. How does that compare to the number of partitions with at most k parts? Okay. You think about it, at most, how many partitions have at most k parts as opposed to having largest part k? How do they relate? You're saying they're the same thing. Why are the number of partitions with largest part at most k the same as the number of partitions with largest part with at most k parts? He's saying reflect this around the main diagonal. Does everybody see that if I took this, these people will probably get upset if I used a permanent marker on the screen, right? But if I did, if I draw here, okay, something from here to here, and I now reflect it, does everybody see that every partition that had a largest part of size k now becomes a partition with parts, with at most k parts to it? Okay, how many people see that? Okay, so this is an example of one of the reasons why integer partitions are fun to think about, because this gives you a picture to draw them with, and a lot of these identities kind of fall out of naturally looking at those pictures. Okay, any questions? Yes?
What does it mean exactly for a partition to have k parts? What do you
K parts is how many, if you look at, let's put it this way. Assuming, let's say, professors wrote papers randomly and uniformly and yada yada, okay? How many professors are there with, if every professor had a different integer partition, how many professors are there whose largest paper had k citations compared to the number of professors that had written exactly k papers? We're saying that that number should be the same. That's the interesting thing about this count, okay? If we're thinking about them as partitions, not as professors, right? Because there's nothing conditioning it on professors. Yes?
Can you repeat the analogy one more time?
Okay, so if you look at this, let's say we take a look at this partition. This is now one where we have 3 dots, 2 dots, 1 dot, 1. That's a partition of what? That's a partition of 4, 7, right? Now, what do I get when I reflect this among the main diagonal? I'm going to get something that looks like this, if I do this right, okay? This was 3. This was 2. Is this what I get when I reflect it around the main diagonal? What is this professor? This professor is somebody who wrote 4 papers, one of which received 3 citations. What is this thing? This is a professor who wrote 3 papers, one of which received 4 citations. Which are there more of? Professors who wrote 3 papers or professors who got at least 3 citations on something? The answer is the number of these must be the same as the number of these, because you can flip any one of these into one of those, right? So that's a proof in some sense that the number of partitions of n with k parts is the same as the number of partitions whose largest part is k. Okay? And this tells me that if you're ever involved with counting and you find yourself in a dark alley and someone demands you to count partitions, there's identities here that kind of fall out of these kind of drawings if you interpret these drawings right. Okay? Any questions? Okay? So you should know about integer partitions. They come up, they're fun to count, and of course if you can count them, you can rank them, you can do whatever you want with it. Okay? Any questions? Let's go through some other objects. Okay? Again, I've got another half hour of objects to give you. There's another kind of a thing that's called a partition that is called a set partition. A set partition is if we go back to my screen here, a set partition of a set here of 4 elements is a way to split the elements into smaller subsets, such that these subsets are disjoint, and the union of them is the original set. Right? Okay, so if we take a look at this thing here, okay, one way we can partition the elements 1 to 4 into 2 sets. We could put 1 by itself and have the other 3 alone. We could have 1 here with 2 and 3 and 4 alone. We could have 1, 2, and 3 together and 2 alone. Okay? Does everybody see that we can take these n elements and partition them into subsets such that the union of these subsets is the original set, and none of these subsets is empty? Okay? What things do you guys know of that would be a set partition? Okay? You guys know about vertex coloring. Okay, have you ever seen a graph and colored the vertices? Like a bipartite graph. How do you tell if it's bipartite? Things are on the left, things are on the right, right? Every time you have a vertex coloring, I claim that it is a set partition, right? Every subset is going to be the set of vertices that get a particular color. In a bipartite bipartite graph, every coloring is going to have 2 sets of vertices, each of which the union of them covers the entire graph, and any vertex is either colored white or black. It's not colored gray, so it's in one of the 2 subsets. Okay? So set partitions are the things we call groupings. Okay? And again, if we want to partition 4 items into sets, 1 item we could leave it in is everything is the same color. What would be a graph where all the vertices can be colored the same thing? Can anyone think of a graph where you can color all the vertices the same color? A graph with no edges. This is the kind of graph I like, right? This one that would be a set partition where there's only 1 part, right? What's a graph where you color where every vertex is going to be in its own part? A complete graph, okay? So we have set partitions can go from the whole set to each item in its own set. Okay, any questions about that? Okay, so set partitions are useful things. Okay? And like I say, colorings I think are naturally thought of as set partitions. How many set partitions are there of n things? Okay, let's go back through the same trick. Now we want to know, okay? Let's come back and count again. How many, if we want to take a look at these things, I guess this is not what I wanted to do. Come on. How many set partitions are there of, how many the number of set partitions of n things into k subsets? Okay? So if I give you the numbers 1 through n, how many ways can I partition them
into k subsets, okay, like this. Can anybody give me a formula for that? Okay, think people know, people realize what we're counting. I'm giving you the numbers 1 through 4. How many ways can I split this into distinct groupings?
For each one of them, you can choose one of every k, so k to the n.
What?
For each element, you can choose to which set it will belong.
Which set it will belong to, okay?
So k to the n.
You want to say k to the n, but is it possible you're double counting? Okay, so it's possible he's double counting, okay?
You could have many empty sets, and you could have many.
You're allowing empty sets, and I think you're also going to reconstruct it in multiple ways.
Yeah.
How many ways are there to do this?
Aren't the Stirling numbers?
What?
Aren't not the Stirling numbers?
Sterling numbers.
Sterling numbers, yes, this is what's counted by Sterling numbers. That's helpful if you know what Sterling numbers are. Okay? What if you don't know what Sterling numbers are? How many ways are there to make, in fact, these partitions? Even if you do know what Sterling numbers are, what would be the recurrence to do this? Yeah?
You can say that if you had one less element,
Yeah?
and you already counted how many ways there are to group them into three sets.
Yeah?
So with K, I don't know, like the Sterling with K.
I see. So what you're saying here, I think, is that one possibility is if I have a set, if I want to figure out what to do with element n, you're telling me if I have k parts to it, I can put it in any one of these parts. Okay, so one possible side you're telling me is this is equal to n minus 1 k times k. Is this right? This is going to say what?
When you put the nth element in a new set.
The other possibility is that the nth element is going to form its own group, right? How many ways are there of doing that? Okay, does everybody see what the idea here is? Now every item is either, we're going to take the nth item. The nth item is either in a set by itself, which means that we can do that how many ways? How many ways we can take it, construct k minus 1 part things on all the remaining numbers, or the largest number is going to have company, meaning it's got to have been put into something that already had k parts, okay, and this is this, okay? So using the Sterling numbers, okay, this is, what we've got here, okay? Any questions about that? Being able to construct recurrences like this is a useful skill, okay? Any questions about how we did that? Okay? Now, if I have a recurrence like this, can I, can I construct rank and unrank set partitions? Suppose I want you to go through and enumerate all set partitions, or generate a set partition at random. How do we do this? We need to be able to rank and unrank these things. How do we rank and unrank these things? Okay? It's the same trick that I've done before, right? We start with all the things where there is only one part, where k is equal to 1, 2, 3. There's going to be a chunk of partitions, okay? We list all the partitions from those that have 1 part to those that have 2 parts to those that have 3 parts, okay? If we come up with a running sum of these counts, okay, we now have a way to
we need to know what's the total number of partitions. The total number of partitions is going to be equal to P of nk as we sum that up as k goes from 1 to n. Those numbers give us an order, okay? If I want to now rank or unrank it, if I want to rank something, again, I take my number and compare it to the running sum of these counts, okay? Based on this, I can go and figure out, what the number of parts is, okay? Now that I know the number of parts, okay, what can I now do with this thing, okay? Well, what do I know about the ordering of these things, okay? Usually the way that you enumerate, set partitions are a little bit more complicated to enumerate. What is the canonical order, okay? My claim would be that you take the parts, you sort them according to the size of the smallest item in each part. Okay, that's the canonical way that I would do this thing. And we notice that there's got to be one part that contains the first item. Okay? And so we know that one is going to go in, based on this, we're going to know the number of items. Okay? Based on this construction, okay, if we now look at any one of these parts, okay, he's saying that to get this count, how did we do this? Well, there were k subchunks corresponding to this, and there was one less subchunk corresponding to this. Based on this, what are we going to know? We're going to know where element k sits. If element k is big enough here, it's going to involve item n. It's going to be in a part by itself. If not, what do we know about part item n? We know which part it's going to be. So if you think through the details, you can do the same ranking and unranking the way that we have talked about. Do people kind of see how I'm doing this? More or less. The details, I can see you don't have to see. Yes?
So the order is based upon the number of partitions of the set?
Yeah, so the easiest way to rank and unrank it would be to have the order be based on go back to the recurrence and have it based on how the counting was done. He counted it by saying there were k blocks of this many things, followed by one block of this many things. Okay? Therefore, if you know what value of x you are in a block, if you are in the last this many things of that block, you know that the last part has to be m alone. Okay? If you were in a higher part here, you know that the largest part is going to be in the 1, 2, 3, 4th, which are up to kth part. You can figure out which part element m is going to be in, and then you recur. That is the idea. The ordering that we're going to use here is based on his counting formula. Okay? And it should be clear that if you use the ordering based on the counting formula, this kind of now falls naturally and you can reconstruct it. Okay? Any questions about that? Yes or no? Okay, any questions? Okay. So set partitions are good things to count. Okay? Any questions? And again, that's basically what I just told you about. Let me tell you about one other class of object that is a thing that you may not... How many people have ever heard of Young tableau? No one's ever heard of Young tableau, okay? What are Young tableau? Actually, if no one's ever heard of Young tableau, let me just tell you what sin you have. Has anyone here ever read... How many of you read Knuth's
Art of Computer Programming books. Is there anybody who's read this or looked through it? I mean, you know, if you look through it, that counts, okay? Okay, good. These are these wonderful books that are at the beginning of theoretical computer science, and you know, that's where I learned about young tableau, was by reading through these things. What are young tableau? Young tableau are going to be a combination of set partitions and integer partitions that come up from time to time and are kind of interesting things to learn about. What is a young tableau? A young tableau is going to have the shape of an integer partition, okay? If we look at this thing, the shape of this thing is 4, 3, 3, 2. That's an integer partition of 12, right? Okay? It is going to be a set partition in that it's going to break, if we have a partition here of 4 pieces, it's going to break the numbers from 1 to 12 into 4 subsets, okay? Where the first subset is going to be of size 4, the second subset is going to be of size 3, the third subset is going to be of size 3, and the last subset is going to be of size 2. Okay, do you kind of see sort of what we're doing? We're partitioning the numbers from 1 to n, where n is the sum of the parts, according to the shape of this thing, okay, with one other characteristic that is interesting, that every row and every column has to be sorted. Okay? So if you look at this thing, notice that every row and every column is sorted. Okay? So what is a young tableau? It is a table of n numbers where the n is given by the shape of it is given by an integer partition, and the numbers have the property that every row and column is sorted. Okay, so these are kind of strange looking, interesting objects. Okay, any questions about that? Okay, you may say, well, who cares about these things? Okay, well, they're kind of general things, and let me give you an example of why you might care about these things before I tell you how to count them. Okay? What if you have you guys are used to thinking about parentheses, right? These well-formed parentheses. Okay? You know that this is position 1, 2, 3, 4, 5, and 6. Is there a way to interpret one of these parentheses by a table that is sorted in rows and columns? Okay? Here I've got 1, 2, 3 sets of parentheses. What if I make it table from 1 to 6? Each one of these parentheses has a position from 1 to 6. What are the positions of the left parentheses? 1, 2, and 5. Okay? What are the positions of the right parentheses? 3, 4, 6. Does this table have to be sorted by rows? Does every row have to be sorted? Of course, we're reading them from left to right. Does every column have to be sorted? Yes. Why? Because it's a wolf. It's a well-formed thing. The left parenthesis has to be, the ith left parenthesis has to be before the ith right parenthesis. Does everybody see that the number of tables here have to be the same as the number of parenthesizations? Okay? So if I knew how to count those number of tables, I would know how to count the number of parenthesizations. Okay? So hold that thought for a little bit, okay? So there are certain things that you can think about, arrangements of numbers and tables and grids that start to be interesting when you can interpret them in terms of these things, okay? Any questions about them? Okay, fair enough. Now we know what a young tableau is, okay? Now, what are young tableaus? They are, again, set partitions, because every number from 1 to n is going to appear in exactly one place, that have shapes of integer partitions, okay? And the rows and columns are ordered, okay? So we can enumerate exactly how many different young tableaux there are, using the same kind of magic and stuff that we've talked about here, if we know how to count them. Does everybody see? If I ask you, construct all young tableau, how would you go about doing it? You would say backtracking, because that's what you say for all of these things, right? But if I ask you to now give me, what is the 96, if I want you to construct a random young tableau, this now feels like a hard thing to do, unless you know how to count them, and then construct them recursively. Then you can do these things with exactly the same magic that we've talked about so far. Does everybody kind of get that idea? Okay? So the heart of the problem is, how do you count how many young tableaux there are of a particular shape? Okay? And this, there turns out to be a nice formula for, okay, that's a little bit surprising, called the hook length formula. What do we know? Okay? If we look at an integer partition, let's make a shape of a young tableau. Let's get rid of this thing now. What is the shape of a young tableau? Okay, let's say I've got something that looks like, let's say bunk, 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 bunk. Let's make it bunk, bunk. Okay? How many young tableaux are there of shape 5, 4, 2, 1? Okay? And if we sum that up, that's equal to what? That's equal to 12. N equals 12. How many things are there? The hook length formula is this magic formula that tells you it's n factorial divided by the product of hook length of the hook length of each position. What does that mean? N here is 12. 12 factorial is my numerator. What is a hook length? If I took any position in here, what is the hook length of this thing? It's 1, 2, 3, 4, 5, 6. So everybody see that if you have a hook that was anchored in this position, it would be of length, basically the number of rows and the number of columns here. Okay? So let's think about that. What are the hook lengths that we get in this table? Well, this, and this have hook lengths of size what? 1. What's divided by 1, what happens? Nothing changes. What's the size of this hook length? 3. Let's write it down here. 3. What's the size of this hook length? 2. This one, 4. This one, 4. This one, 6. This one, 3. This one, 6. This one, 8. I'll trust you. So 12 factorial divided by 8, by 6, by 4, by 3, by 6, by 4, by 2, by 3 is going to be how many of these factorials we have. how many of these tables we have. Okay? Any questions about that? Okay? This is a powerful, crazy thing, right? Now, why does this work? Let's just think whether it works. Okay? First of all, how many? Let's just check it out, because before I do something like that, I want to really be sure. What if my table is like this? How many young tableaux are there of shape n? 1. What is that going to be? That's n factorial divided by what? N by n minus 1 by n minus 2, dot, dot, dot. How many are there? 1. Okay? That works. What if I make it like this? Same thing. It's going to work the same way, right? Why does this formula work? The exact reason why is complicated. But an argument that is close enough is to think about it is what fraction of young tableau. Okay, if I consider, let's say, if I have a table of n cells, how many ways are there to map the numbers 1 to n to those n cells if I didn't care about the ordering? N factorial, right? If I want to now look at an assignment, what fraction of those things should have the biggest one in this position? Suppose I randomly assign numbers to this table, kabunk, okay? And now I ask myself, what fraction in a young tableau, the smallest number, I guess the smallest number in this row and column is going to be in the corner, right? What fraction of the random things are going to have that smallest number in that corner? 1 over the size of the hook length, right? So if you assume some independence here, this gives us exactly the way to count those. Does everybody get that? Now, why is it independent? That I don't want to test. That sounds complicated. But suddenly this formula doesn't look like it's from Mars anymore, right? Does everybody kind of get the sense where it's coming from? Okay? Fair enough. Now, if I know how to count these things, is that enough to know how to rank them and unrank them and do everything else? The answer is yes. Okay? So you guys, if you now know how to count how many young tableaux there are, and therefore you know how to rank them and unrank them and anything else that's there. Okay? Any questions about that? Now, how many of these things are there? How many parenthesizations are there? Okay? Did you guys ever count how many parenthesizations there are on a string of n even things and n odd things? I mean, if you have n pairs of parentheses, how many legal things are there? There's the Catalan numbers, right? What are the Catalan numbers? Okay, that helps you the same way knowing that it was the Sterling numbers helped you until you knew how to count them, right? How many ways are there making n things into parentheses? Okay, what is the idea going to be?
It's going to be look at the tableau.
Okay, one way to do it is to look at the tableau.
Is 2n factorial?
What is the way, the hook length formula going to tell you how many parentheses there are? What is it going to be? Well, there's going to be 2n factorial numbers that we have. 2n numbers, right? I guess actually, right, in this case we have 2n numbers. 2n factorial is the numerator. What is the product of the hook lengths?
The bottom row gives us
Well, the bottom row gives you 1, 2, 3, this is n, n factorial. What does the top row give you? This gives you, in this case, it gives you, well, let's just be precise here. This is going to give me n plus 1. What's the next one going to be? 2 less than that. It's not an n factor. It's not a factorial here. Yes. What is this going to be? This hook length was of length 4. This one was of length 3. Wait, no, this hook length was of length 5. This hook length was of length 3. This hook length is of length 1. 2, 3, 4. Okay, okay, you're right. So what is this going to be? This was going to be what? N plus 1 factorial. Okay? Now, what is this? Let's go back to how you did count the Catalan numbers. Okay? If we go back to the Catalan numbers, what was the right way to count them? Okay? The right way to count the Catalan numbers was to come up with a recurrence relation. What is the recurrence relation? In any legal parenthesation, there is a first place where it is perfectly balanced. Does everybody agree? Suppose the balance point was after k pairs of balanced parentheses. What is the total number of ways of making parentheses? Okay. It's the number of ways of, if C of n is the number of parentheses on n parentheses, it's going to be the sum over all k of, if the first breaking point was after k parentheses, the number of ways of counting k parentheses, times, now you've got n minus k parentheses left. That's basically what you have left. The left formula followed by the right formula.
Sorry, shouldn't it be C of k minus 1 times C of n plus k?
C of,
Because if it's the first correct parenthesation, then it must be wrapped entirely.
okay, so there is this question of whether we're counting things where you're allowed an outer parenthesis or not.
Right.
Okay?
And if it's not, then it cannot be the first correct parenthesation, because it must be a concatenation of 2 correct.
Right. I see. So you're saying, okay, so what you're counting here is the following. If there's a break, we know that this matched with this.
Right.
There's this much stuff inside and this much stuff on the other side. And that's why k plus n minus 1 minus k does not add up to n. It's that outer one that we didn't have. So if we look at this recurrence, if you solve it, this is what you call it, the closed form for the nth Catalan number is. And sure enough, it is our 2 to the n factorial divided by n factorial divided by n plus 1 factorial. Any questions about that? Okay? So I think I will send you into lunch with the thoughts of young tableau. You know how to count them now. This formula kind of comes in handy because it's really powerful. It counts a lot of weird things. Okay? And not everybody knows about it. Okay? Any questions about young tableau or anything like this? Okay, so I'm going to send you guys into lunch. I would like to have lunch with you guys today. So I've been sneaking off to lunch, with professors, eating at better places. But today I'd like to eat with you guys. So somebody find me and show me and walk me over to where you guys are eating. And I'd like to sit with you guys and get to know you. Okay, thanks a lot, and good luck on the conference today.